Hello and welcome to Project 152, your weekly exam prep. Now every week we go through past questions from the QCAA. If you stick with us for the whole year, you'll have done every single external exam question that the QCAA has ever put out. Link in the description to last week's questions, this week's questions. This week is week 14 and let's get started. Every question we're doing today is a tech active question, but I might just do this one without my calculator because it's really a skill that we should be able to handle. Now we're looking for the solutions of this. Now if it's z to the 4, that means there's going to be 4 solutions, and you can see every single option has 4 solutions. Now importantly, 4 solutions equally spaced around a circle, which means that there's going to be 90 degrees or pi on 2 radians between every single solution. And no real help there because every one of these is equally spaced, 90 degree angles between them. Okay, let's jump into it. So z is going to be equal to the 4th root of 16 cis 2 pi on 3. Now, in order for us to do that, we're doing 2 things. We're taking this 16 and we're finding the 4th root of 16, and then the argument 2 pi on 3, we're dividing that by 4, which is the same as just multiplying the denominator by 4. All right, 4th root of 16, 2, 4, 8, 16. So the answer is 2 there. That's going to be the modulus. Now, if we look at our answers, this circle has a radius of 4, this circle has a radius of 4, whereas this one has 2 and this one has 2. So our answer is this one or this one. And then we have cis 2 pi on 12, which is the same as pi on 6 when I simplify it. Okay, that means that 2 cis pi on 6 is one of my answers. And you can see this one here, that's 2 cis pi on 6 right there. So that means that my answer is C. Now you might waste a bunch of time finding the other 3 answers, but there's really no need to do that. All you need to know is that one of the answers is this one, and the other ones are 90 degree angles between our 4 answers. Now given this is a tech active question, I was interested in what my calculator could actually do. So I did the 4th root of 16 and then a little angle sign 2 pi on 3. So that's how you can type in polar form. It gives me root 3 plus I, and then I just converted that answer to polar form, and I get this, which is the same answer as this. Now, interesting, it only gives out one answer, which is that, but there are actually 4 answers. So your calculator isn't spitting out all 4 answers, which is a little bit of a shame, but because it spits that out, we can then make this choice because we know that the 4th root of a complex number will spit out 4 solutions. All right, we're going to celebrate that one. Next question. All right, so we've got a plane containing the origin and the points 1, 2, 3 and 3, 2, 1. A vector normal to the plane is what? All right, so we've got the origin 0, 0, 0, and then we've got 2 vectors 1, 2, 3 and 3, 2, 1. And we're trying to find another vector. Let's go for a different color. That makes a right angle to those. So we should be thinking about the cross product, and because it's tech active, we should be able to use our calculator to figure out the cross product pretty quickly. So it can get confusing to how to do this, but I'm going to try to speed it up. Now we've got the option here. That's when you want to do an operation. So I want to do an operation. I want to do a matrix or vector operation, and the operation I want to do is a cross product, which is sitting right here. Okay, and now I want to enter 2 vectors, so I'll get out of here. Now all the entry stuff is here. Don't click this button because that takes you like to this thing. We're not going to use that. Instead, we're going to go math, and we're going to enter some vectors. Now, interestingly, when you enter vectors, you've got to enter them as 1 by 3s. You've got to enter them like this. And when you want to do a cross product, you do that, you do a comma, and then you do another 1 by 3. I don't think it's closing up the bracket for me, so I'll do that. And then I just enter these numbers, 1, 2, 3, 3, 2, 1. 3, 2, 1. Now I've pressed enter and I get -4, 8, -4. Can we see -4, 8, -4? No, we can't. Okay, so what's gone wrong? What's happened? How come I'm doing the cross product, I'm doing everything correct, but I'm not getting the answer I want? Well, I like this question because it says we're finding a vector that is normal to the plane. And I've said, well, here's my vector here. But there's actually like an infinite number of vectors that are normal to the plane. Could be a much longer one, could be a much shorter one, could be one going in the other direction, etc., etc., etc. So the answer that I've found is -4, 8, -4. And so the question is, can I take this, multiply it by some k value, and that'll mean that it'll grow or shrink or change direction if it's a -k value, and have one of these answers spit out. And I can see it here. If I multiply this by -1, so if k is equal to -1, -1 times -4 times 8 times -4 will be 4, -8, 4, 4, -8, 4, and the answer is A. All right, so interesting question. I like it. I wish they'd made it a little more difficult. And what I mean by that is, if I'd written my vectors in the other way, in the other order, 3, 2, 1 first, and then 1, 2, 3, it would have directly spat out this answer. And so I wouldn't have had to go through this like extra step of trying to figure out the k's. My preference would have been these answers being like, let's say we multiply everything by 3. So like this wasn't 4, -8, 4, it was like 12, 24, -24, 12. And then you'd have to make the extra leap of saying, no matter what answer comes out of my calculator, I've got to find whatever that k value is. So, but fun times. Let's celebrate. All right, so question 11, it's a simple familiar question. We got 3 parts. We got a 1 marker, a 1 marker, and a 2 marker. Important to note, if you ever see a question that's worth 1 mark, you don't have to show a bunch of working, you've just got to come up with the answer. And the reason I say that is because it says, determine the coordinates of point A here, and I have a graphics calculator, so this is going to be simple. All right, let's jump into this. So it's a sec graph, and you're going to wonder like, okay, there's no sec button. That's okay, because you should know that sec is equal to 1 over cos. All right, so let's enter it. We've got -1 plus, and then when I say sec is equal to 1 over cos, this whole bit is 1 over cos x over 5. So it's going to be an interesting little nesting operation here. We got 1 over cos in brackets, and then here we've got x over 5. So another set of brackets, x over 5. All right, I think that's it. And then the other one we're going to graph is pretty simple. I'll just type that in. All right, that's great. Let's draw it. So when I draw it, I get something that looks like this, which is really, it doesn't seem like that's what I want it to look like. Maybe it's like something going on there. So let's just change our view window so that the Y max is like larger, maybe like, I don't know, 20 or something. See if that fixes it. Okay, probably not a great scale to work with, but it's good enough for my purposes because I can see this nice clear intersection point. So gsolve, intersect. All right, there's my first intersection point, 0, 0, which makes sense here. And then my other intersection point is right there, 7.00, 4.904. All right, so that's 1 mark. That's it. Determine the coordinates of the point. I did it. Okay. Now it says calculate the area of the shaded region. Again, it's 1 mark, so our calculator should be able to do that for us. Let's do a gsolve here, and let's go for our integrals. And when I go for our integrals, it gives me a bunch of options here. I'm going to use the intersect option because it'll jump to the intersection, 0, 0. And so it says select lower limit. You can just type it in, but also that's exactly where I want the lower limit to be. So execute. And then it'll say select upper limit, and then if I arrow across, it'll take me to the next intersection, and I'll execute that. And then it gives me 2 values here. So it's important to understand what the 2 values are. This is the negative, this is the actual integral, this is the actual area. Sometimes these are exactly the same. Sometimes one's negative, sometimes one's positive. Sometimes the numbers are different. I'm not going to get into what's going on here, but the area is what we want, 6.14. Feels a bit naughty saying I'm not going to get into it here. We're talking about signed area. If some of it was like, if it was overlapping, doing like weird things like this, then these two values would be very different because this is treated as a negative area and this is treated as a positive area. So this just gives you like the value positive minus negative kind of thing, whereas this gives you the actual area just by adding the absolute values together. All right, that's probably more than I needed to say, but I just wanted to put it out there. All right, finally it says the shaded region is rotated around the x-axis to form a solid of revolution. Determine the volume of the solid formed, and we're going to get 2 marks for it. So we've got to show some working. Now this is the formula you should be very familiar with, but it's also on your formula sheet. So here we are. Volume of solid about the x-axis is equal to this. Now we're finding the volume if we rotate this area around the function, and some people think they're going to like weirdly subtract one from the other the same way that you can with area, but you can't really do it quite like that. Sort of, but not quite. What we're essentially going to do is rotate this one, the top one, around, and then we're going to rotate the bottom one around, and then we're going to subtract one of those values from the other values to get the leftover bit that's been rotated around. I hope that makes sense. All right, so let's find the volume of the large one around. So it's going to be equal to volume equals pi integral between here, so 0, and here, and that's the x coordinate, so 7. All right, now I didn't even bother to figure out what the top one was. Let's find out which function the top one is. All right, so the blue one is this big nonsense one, so let's double check that. Okay, so the blue one's the bottom one, which means the red one is the top one. So this is going to be 0.1 x squared, but then look at our formula. Don't forget to square it. And then with respect to x. All right, now some of you may be shouting at your screen that there's like an easy way to do this. Fine, I will mention it in a minute, just calm down. Okay, we're going to leave that for a while because I am going to sort of build everything and put it back together. Now, what about the volume for the lower one? Well, it's exactly the same, but instead of this function, it's this function. Okay, this is great. So I'm finding the volume of the top one like this. I'm finding the volume of the bottom one with this move here. So I could type this into my calculator, get an answer, type this into my calculator, get an answer, and then subtract one answer from the other. So the reason I said people are going to be shouting at their screen is because I can sort of write this as a single integral. Let me just write it all out as a single integral. So this is what I'm talking about. We can write it all out like this. So rather than calculating this, getting an answer, calculating this, getting an answer, and subtracting one from the other, we can write it out as a single integral and do it that way. If you want to check this out yourself, write this minus this, and you'll notice that you can take pi out as a common factor, and you'll notice that you're taking the same integral of both, so you can put them within a single integral. Now, all of that said, why am I like not too concerned either way? Because I've got my calculator, I can put this in and just get an answer. I can put this in, just get an answer, and subtract one from the other. When would this be useful? It's possible that this would be useful when a bunch of stuff ends up cancelling each other out. Probably much more useful in a tech-free exam where you don't want to end up doing a bunch of multiple calculations. So having this skill, very useful. I would argue maybe not very useful in a tech-active exam, however. All that's left to do is to just type all of that into our calculator, which is going to be a bit of a mission. So I have typed it all in. Now, a couple of little notes here. When you type it in, you're going to square it, you're going to square it again. Big thing in brackets, not sec, because you don't have a sec button, so cos, x over 5, nesting that, squared with respect to x. I get an answer of 69.75. In hindsight, I really wish I just hadn't have done this. I really wish I'd just typed this in once and then typed this in again. If I type this in, I can get one answer for that, and then I can just delete that and enter that in, and then that'll give me the second answer, and then I just subtract one from the other. I think that would have been easier than typing all this out, because very prone to making a mistake when I do that. All of that said, I didn't make a mistake. The answer is 69.76. Now, who knows if we're going to get some marks for this, but we're going to write 69.76 units cubed, right? Because that is what we're doing. We're doing a volume of solids of revolution. They didn't give us like centimeters or meters, so we don't know what the units are, but we can say that whatever it is, those units are going to be cubed because it's a volume. All right, so on this, we've got a mark for this, we've got a mark for this, we've got a mark for coming up with this formula, and then we've got a mark for coming up with the volume itself. And whether you came up with this formula, it doesn't really matter. It doesn't look like they care whether you get units cubed written there or not, but probably a good practice. All right, let's celebrate, and we've got one last question. All right, so we've got one last question. It's a complex, unfamiliar question, and I'm feeling a little bit philosophical today, so I want to let you in on a secret. When maths teachers, not students, maths teachers look at complex, unfamiliar questions, they do not know how to solve them. So every time I make one of these videos where I talk about complex, unfamiliar questions, and I'm like, first you do this, and then you do this, and then you do this, I don't know. If I'm doing the question myself, I've got to scribble some stuff on paper, try some things, maybe go down some weird little sidewalks and different places until I figure out the answer. So don't be intimidated when you look at a question you don't fully know what's going on. You've just got to start. And then maybe after you make a start, you'll do one step, and then you'll do another step, and then you'll do another step. Okay, so what do we have? We've got this big long equation here. And then we've got some other stuff going on here. Okay, now, the first instinct I have when I look at this is, hey, there's a bracket, and then there's another big long bracket. I can see like a weird pattern going on here, pluses and minuses, pluses and minuses. 1 minus z, doesn't mean a lot to me. I wonder what would happen if I managed to expand these brackets. Okay, let's see what would happen. We'd get z times z to the 15, so z to the 14 would make z to the 15. Okay, and then the next one, z times negative z to the 13 would make negative z to the 14. And then I can see another one, z times z to the 12 is going to make z to the 13. And then I think we can understand the pattern that's forming. Because this is in a pattern, negative, positive, negative, positive, negative, positive. If I multiply everything by z, I'm going to get the same pattern, negative, positive, negative, positive, negative, positive. So I won't write them all out, but I'll do the last two as well. Z times like z squared would make z cubed. And then the last one would be z times negative z, which would be negative z squared. And then that's where that stops. Now, what about this next bit, right? So I've got like, 14 terms there so far. What about here? 1 times z to the 14. Let's use a different color. So that's going to be positive z to the 14. And then 1 times negative z to the 13 is going to be negative z to the 13. And 1 times positive z to the 12 is going to be positive z to the 12. And we can see a similar pattern forming, dot, dot, dot. And then 1 times z squared would be z squared. And then 1 times negative z would just be negative z. Okay, what have I got? What's going on? I've expanded this whole thing, just leaving some gaps here because I know what happens in those gaps. And I know also that all of it is equal to 1 minus z. Okay, what do I see? I see negative z to the 14, I see positive z to the 14, I see positive z to the 13, I see negative z to the 13. I see cancelling, cancelling. That z cubed is going to cancel. The z squareds, negative z, positive z squared, they're going to cancel. So what am I left with? I'm left with, and let's just move it all over to here, z to the 15 minus z equals 1 minus z. How cute's this? Now those negative z's cancel each other out, and I'm left with z to the 15 equals 1. Alarm bells. Oh, yes. Alarm bells. Z to the 15 equals 1. That's a root of unity. I've got a picture that I can draw now because I know that there are going to be 15 solutions to this, 15 equally spaced solutions around a circle. All right, so what have we got? We've got one of the solutions is just 1. Solutions Z equals 1. And if you're screaming at your screen right now, don't worry, I will fix it. Z equals, now 15 equally spaced solutions. So my next solution is going to have still a modulus of 1, but the angle is going to be 2 pi, because that's how many radians there are in a circle, divided by 15. So cis 2 pi on 15. Okay, and then I'm just going to keep going around the circle. So one of the solutions is 2 pi on 15. The next solution, I don't need this 1, it can just be cis. The next solution is going to be cis 4 pi on 15. The next solution is going to be cis 6 pi on 15, because I'm adding another 2 pi on 15 until I'm going to get all the way around the circle. That's all of them. Okay. Now, there's actually too many here because cis 30 pi on 15 is equal to 1, because I'm just looping back on myself. So, I have exactly 15 solutions here. Now, I'm going to tell you the truth, and I'm going to tell you that the first time I did this question, I used these solutions to start working through these pieces here. And finding the solution with the maximum possible real part. And solution with the maximum possible real part, according to this, is this one right here. Right? Now this is wrong, and I'm going to show you why it's wrong, but this is how I proceeded. I did this, and then I also found the solution with the maximum possible imaginary part. And the maximum possible imaginary part is one of the solutions that's like here or here-ish. And you can test out this one and this one, or you can just, because you might not be comfortable thinking in radians, because it might be easier to think in degrees, each of these is 24 degrees. So we go 24, 48, 72, and then the last one here is like 72 plus 24, which is 96. So this one is going to be the one with the maximum imaginary part, right? I'm wrong. And the reason I'm wrong is this sneaky bit here. And so let this be a lesson to you. You've got to always check your domains, because it says that this equation's true, but only where the argument is a greater than 0 and less than pi. And so all of my solutions, I can't use all of them, because these ones and all of these ones, they have arguments greater than pi. So they're out. Also, this one has an argument less or equal to 0. So that one's out as well. Okay, so let's get rid of those, but I really wanted to show that to you to make sure that you understood that, hey, you can get all the way to the end of the problem, find out that it's not working, mine wasn't working here, and then revisit it, reread things, and make sure that you figure out what happened. So it comes down to these solutions now, right? And so now let's revisit it again. Let W1 be the solution with the maximum possible real part. All right, now these solutions can all be written here, 24, 48, 72, 96, and whatever the other ones are. But these are the only ones that really matter to me, because the solution across these equally spaced solutions that has the maximum possible real part is this one right here, right? You can see that's the real component. We're drawing pictures, we're thinking about it. The real component, that's the largest one. So we let W1 equal this one here, cis 2 pi on 15. Now, they say that W2 is the solution with the maximum possible imaginary part. And that one's going to be here. The 1, 2, 3, 4th solution, 1, 2, 3, 4. This one right here, cis 8 pi on 15. Now I'm doing this because I can draw pictures and I know that the angle 96 is closer to the angle 90 than the angle 72. So this must be my answer. If you don't want to do that, you can just calculate the imaginary components for like all of these if you wanted to and figure out which one had the largest imaginary component. That would be pretty painful though. So we're going with this way. All right, now we need to show that W1 to the power of 4 over W2 is an integer. So let's try it out. We've got cis 2 pi on 15, and we're going to raise that to the power of 4, and then we're going to divide it by cis 8 pi on 15. Okay, raising cis 2 pi on 4 to the 15. Actually, we could just type that into our calculator. That would be fine, but let's just not type this into our calculator because, again, this is almost as fast to do it by hand as it is to do it on our calculator, I think. We multiply this by 4, so we get cis 8 pi on 15 over cis 8 pi on 15. And we're dividing something by itself, and that's going to be equal to 1, which is an integer. I have shown that that is true. Maybe we can't use our calculator because it does say show that. I feel like maybe we do need to show sort of algebraically that that's true. So it's a 5-mark question. What are you getting marks for? You're getting marks for doing this. You also get a mark, and they say correctly showing the positions of the solutions. And that could be this list of solutions here. It could be like graphical here. It could also be saying that the solutions are 2n pi on 15, 2n pi on 15, something like that. You also get a mark for finding W1 and W2, so that's 4 marks in total. And finally, you get a mark for showing that the whole thing is true. A really cool question. So many of you out there are way smarter than I am. Like, you've got like a raw processing speed. The only way that I ever beat you in any kind of mathematical competition is with experience. When I see negative, positive, negative, positive, negative, positive, negative, positive, I know through my knowledge of like a bunch of questions that I've done in the past that there's some sort of trick to this that involves a bunch of cancelling. 9 times out of 10, if I see negative, positive, negative, positive, negative, positive, I know that at some point in the future, everything's going to cancel out and I'm going to end up with something nice and neat. The more of these sorts of questions you do, the more you start to spot these kinds of tricks that teachers play in these exams. So keep an eye out for this one. It happens I wouldn't say all the time, but it is like a nice, neat trick to use in complex, unfamiliar questions. Let's celebrate that one. So that's another week down, another Tech Active week down. Link in the description for the next week's questions. You know how it goes. Have fun with it. Let me know what you thought of those questions. Let me know how you're tackling them. Let me know anything. I'd love to hear from you if you've made it this far in the video. That would be super awesome. Comment below. Catch you next week.